Good evening. My name is Daniil Grebenkin, and my academic advisor name is Bondarenko, and our work is devoted to speech recognition tasks. First of all, it needs to be said that the modern speech recognition systems use end-to-end approach. It means that there is a solid neural net which gets the audio speech information as inputs, and it gives the transcriptions as outputs. And end-to-end approach has a different advantages and that's the reason why it's so popular. First of all, there's no need for separate formation of a dictionary and training of a language model like it was in classic models like Caldi or Simius Things. Secondly, if it's a neural net, we can always use pruning or quantization techniques to reduce the size of the model and to increase the speed of its work. And finally, we can use some big pre-trained model, and if we have a small amount of audio data with the speech with the words from a specific domain, we can use a transfer learning to adapt these big models to this specific domain. Most of the end-to-end systems are transformer based. They have transformer based architecture, and means that all of them most of them uses self-attention algorithms. But self-attention algorithms have some disadvantages. First of all, well, it was said today that it has some problems with long sequences. I can add that the overfitting on training set can happen. It means that if you train on sequences of a certain length, it's not a guarantee that would be that would have a good performance on the sequences with shorter or longer lengths. And the second was the research where the ability of recognition of some regular languages was researched, and the limitations of recognition of some regular languages were discovered. It means that self-attention had a worse performance. I mean, it couldn't recognize all non-star-free languages and some star-free languages. And this disadvantages made researchers to find some decisions how to make them to do any analysis of some analysis of self-attention. One of them was associative memory. The concept of associative memory is based on ideas about human memory. Some objects can generate areas of memories associated with these objects. In the terms of associative memory on neural nets models, it means that there are two types of it: auto-associative memory and heteroassociative. Auto-associative can complete or correct the input image, but it cannot associate the input image with another one. And heteroassociative memory recall an associated piece of input image. So it's just get the image as an input and make another image as an output. Neural net model of auto-associative memory was proposed by John Hopfield in 1987, and it was a kind of a recurrent neural network which could recover the whole image by its fragment. For example, if it was in a real image, a picture, it could recover it with input fragment. The neural net was trained to concrete images, and it just uses the Hamming distance to find the difference between the input image and the trained image. And if we talk about audio, the augmented data can be used as an input, and the output would be a clean data, or a fragment of input data can be an input. So, but the main problem of Hopfield networks was the limited maximum number of images was linear dependence. You can see it on the screen. And that was the problem for many years until in 2016, in the work dense associative memory, the researchers John Hopfield and Krotov, they modified the energy function, which described the behavior of Hopfield networks, and it makes it possible to make the exponential dependence on the number of neurons. The main hypothesis of our work is that, and this modification, it was called dense associative memory. The main hypothesis of our work was that dense associative memory is better than self-attention because of the speech recognition model can be trained to the images of speech representations, which can be recovered from any type of input audio. And it means that it should be resistible for any augmentation, for reverberation effects, for background noises, for dialects, etc. The main goal for our works was to test the possibility of replacing multi-head attention to dense associative memory layers in the for the speech architectures like WAV2. We used a small amount of speech audio data to compare the classic architecture and the new modified one, and confirmed our hypothesis from the previous slide. Well, what is WAV2? Well, in this screen you can see the architecture of WAV2 model. The classic WAV2 model. It works in the way that the model gets the input audio. It can be a spectrogram. Then the convolutional neural networks layers gets as an inputs, and it made quantized representations, speech representations, and they are the inputs for a transformer part. The transformer part is trained on unlabeled speech data, and it's it gets the unlabeled speech data. It masks some of the fragments and use them as labels. This technique is called self-supervised learning. So, as I said, we trained two models. The first step was to train them in the self-supervised learning, to train the transformer part of WAV2 using self-supervised learning. We used a small part of Sava dataset YouTube, 2,000 hours. Then, and the last step was to fine-tune these models on labeled speech data. We used Sava dataset devices, 100 hours. The implementations of dense associative memory layers were used from HF layers library, And it needs to be said that we used a small amount of data to understand if it's sufficient to modify a classic web-to-vec architecture. We wanted to understand if it's if it would be useful, and then okay, I'll say it later. We used several data sets for testing, Boxforge RU and Sberg devices goals, and we've chosen character array various character array metrics for this test. So you can see that the model of with modified architecture had the better error rate, and we try to understand why this happened. We took Boxforge audio data for our analysis. First step was to extract last hidden layer outputs after processing of input audio of every input audio of Boxforge. We made it for each model. Then we had to find the bounds of each sound in the input audio. We use transcription and forced alignment technique for it, and to find the more clear bounds, we used the good big speech recognition model of the large RU goals. So there was a condition that the letters would be the labels of our sounds. Then these time bounds were used to collect arrays of corresponding embeddings. Means that there could be several embeddings in this time interval, which was found by bounds. And these arrays of embeddings were averaged. We tried to understand what did we get, and we used UMAP projections as a visual interpretation. Well, for example, for stressed vowels. Well, in this picture you can see UMAP projections for classic model on the letter A, and Hopfield tiny model that will be letter B. And when you see it, it's very similar to the rational vowels chart. Well, you just have to reflect them horizontally, and that will be that would be the same structure. So what else we can say? That the classic clusters are more stretched from each other. But then we tried to evaluate this clustering with with the cluster silhouette index, which shows the object similarity to other objects of the cluster. First of all, it's found the edge of average distance between the ETH objects and other clusters objects. Then the smallest average distance from these objects to all points in any cluster, which doesn't contain this one. And then there is a formula which shows the finding of silhouette coefficient value. Well, it's the values of silhouette coefficient can be distributed from -1 to 1. If it's closer to 1, it means that objects are well clustered. If they are closer to -1, it means that the objects is more similar for neighboring clusters. If it's closer to 0, it means that the object is near the bounds of the clusters. So we get this values of silhouette coefficient for every classes of our embeddings. We make classes of stressed vowels, as I've shown the UMAP projections of them, unstressed vowels, sonorants, occlusive consonants, affricates, and fricative consonants. And the Hopfield model had the best scores in most of the classes except of sonorants and fricative consonants. To conclude, I would like to say that we think that using the dense associative memory for self-supervised learning in speech recognition is more efficient because in a way when we train the tiny models with different architectures on a small audio data set. And we confirmed this this thought with testings on different data sets, but it's not really clear why it had so strange results on the on different classes of phonemes, sonorants and fricative consonants. We hope that our further research with big amount of data will make it clear, and it should be underlined that this experiment is the first of a big series. And we also want to try to test these models on a set of augmented data with different settings of augmentations. And the first, the last perspective is modeling specific associative dependencies among the phonemes of many languages to create a multilingual speech recognition model. Thank you for your attention.
Thank you for your presentation. The first question that comes to my mind is, why have you compared the character error rate but have not compared word error rate?
Because
why it is not mentioned there?
Well, we think that our task was the self-supervised task is to make the transformer to learn the speech representations. That it means that it should make the letters as an outputs, and it's we didn't expect that there would be any linguistic information for that. That's why we use character rate, but not the word array.
More questions? So I may? May I? Okay. Yeah, so I have two. The first one is, what are upstream tasks you used for self-supervised learning?
Upstream?
Yeah, like what are tasks which you used with unlabeled data and the supervised learning?
We made the transformer part of Outlook 2 to learn the speech representations, and we used unlabeled data for that. We used the part of labeled data were masked, and the representations under the mask were used as labels.
Okay, but nothing like sentence completion, nothing like phrase completion.
Phrase completion?
Phrase completion, like phrase, yeah.
Phrase?
Yeah.
No, that was on the level of sounds, so we didn't use phrase.
Okay, word completion, the same.
Word completion. No, that was task about sounds, not about phrases or words.
But like words are sounds in some terms.
I'm sorry, I have a small answer. For clear experiments, we use same losses and same tasks as in classical wave-to-wave tool. So we have two tasks for self-supervised learning. First task is classical masked language model for transformer part of wave-to-wave, and second task is based on contrastive learning for more different speech representations on convolutional and quantization part of transformer. So we use these losses for wave-to-wave classical and for wave-to-wave Hopfield.
The last one you said contrastive learning. Okay. Yeah. So actually, this is closes my second question.
Contrastive learning was used and the
Mhm.
second step,
Yeah. Okay.
fine tuning.
Thank you.
Thank you for your talk. I have a question regarding the image you have shown to us, where we compare the representation you have achieved and some other regularly achieved. Yeah, this one. You said that it is the same with some transformation, small
Yeah, yeah.
transformation. I have a question like, have you tried to numerically describe this difference or similarity? So is it, for example, it could be done using some clustering measures or some other measures available? Have you tried this?
No, we only tried to cluster silhouette index. Coefficient.
Okay, I just suppose that this could be interesting. So if you show numerically that it is the same, it's like really great achievement. So you've shown that you discovered the presented structure without using any prior knowledge.